So I feel a bit like end of a long period, and I didn't really want to give a highly technical talk, and also I didn't want to give something which I've theorem proof, but I do want to talk about something which is I consider very important. So this is a sort of ideas talk with a little bit of maths. Okay. So I'm going to set a little question for everybody. Now, here we have University College well represented. Let's just suppose we have University College, and we also have, let's say, London School of Economics. Yes. Where are you?
Durham.
Durham. No, I'm not doing Durham. I'm just doing. I'm just doing. It is a bipartite. So the question is, what's the connection between the Department of Medicine, let's say University College Hospital or somebody associated with it, which is in Gower Street in London. Great goal by Harry Kane, wasn't it? Oh, that was, and let's say the Economics Department at London School of Economics. But this is actually quite a serious point, so I'll leave it to you as a kind of brain teaser to see if there's any connection between the two. Okay, the other thing, you can see that the answer is really in two. The other thing which drove my interest, and there's two topics here. There's the two main topics of bias, and also, if I had time, I definitely want to talk about causal models. So, from my point of view, my thinking of this group, and I should mention that my co-authors, this is quite nice because Ava was my PhD student and Elena is Ava's PhD student, and Ava just got married last week, so that's quite nice. So the really serious point, to my mind, is if you have big data, and there's no data in this talk, okay. This is a big data talk with no data in it, just ideas. The really serious point is, how do you build, if you have a big complicated data set, how do you build causal models to do science? And I will try and address both points. And so the two important words here are bias and causal models. In some sense, you must defend yourself against biases. Actually, we've had in the whole of this workshop, we've called bias discrepancy in a way. And so, let's see. This is again a slide with data without data. So you've got a kind of stack, which is a big data set, out of which you're going to pick an experimental design. But of course, you have the world, the real world, outside. That's really the issue. I'll return to this point later on, because the social scientists, the social science work, and I have some quite a good set of references at the end. The social science are rather conservative. They like to go from a subpopulation to a bigger population, like a population of some large population, I think, in a town. They're very nervous of going from the big population, let's call that the big data, to to the wider population. They're very nervous about making inferences, and a lot of the subjects, I'll return to this in a moment, a lot of the subjects are driven by that nervousness that the social sciences have. So, I've just got, the whole talk is in a sense just got one message. And if we're going to defend ourselves against bias, against biases coming in from various sources, we need bias models. Now these models are bias models which may be included in our big model, all right? Or they may be some kind of, I don't use the word Bayesian, some kind of vague idea that we're going to be attacked by hidden variables. If you think about it, we can do this example now. Why does a university college randomize its clinical trials? Well, I'll have a whole list of reasons in a minute, but it's to guard against hidden variables. So, just in case the color of your hair, of a patient's hair, has an effect, they want the same number of, say, red-headed people in the treatment and in the control, so that then they cancel out. So, bald ones. Well, I didn't want to be baldest for obvious reasons. but you've mentioned a new prejudice, which we should both be on the committee to defend. So here is.
I remember being part of a big smart meter trial where there were all kinds of exclusions. The best one of those was that they didn't give smart meters to people whose first language is Welsh.
Oh, okay. Thank you for that, because that reminds me of something I haven't mentioned on my list. One reason this problem is very difficult is not for the social science, or not even for the physical science. It's because with the advent of new technology, and I'm involved in putting hot water into people's homes and running experiments on smart meters, this topic will be even more important for what are called socio-technical things, where you've got people and machines, something called human factors. So that's why we need to be good, because the scientists have one sort of causation and the social scientists have another sort of causation. So I'm going to have a simple bias model here. So theta, which will be, and it's a bit of a sexist talk, but theta will be female, all right, in a way that I will make clear, and phi will be male. And phi, and not because phi is that males are biased, or that may be the case, but because I need to distinguish between these two parts of the model. Now, I now need to do classical optimal experimental design, which is a number of experts in the room. So when we do experiments, as you all know, you do the matrix version, y equals x theta plus epsilon, and the design matrix. This is, we call it the design matrix. Columns are functions, rows are points, all right? Very easy. This is design matrix. Everywhere, if you're doing nonlinear regression, you've linearized. So then we normalize. So we get rid of sample size in the classical Kiefer-Wolfowitz optimal design theory. We kill sample size, and then we do something whose correct name I only learned yesterday. We do convex relaxation. We replace the points by measures, and so we would write. I'll do it just for the first model there, theta, the integral of fx transpose, rank 1 matrix, integrated with respect to over some design region. And so this would be 1 upon n times the sum. So this case would, there should be an arrow here. This case is the measure which puts mass 1 upon n at every point. So this is very, yes.
One point here, on your top equation there, you have x for the female variables and z for the male variables.
Yes, but I don't want, I think we...
Does that mean that you know which are male and female?
Yeah, next slide. Next slide,
Okay.
next slide. So what I've done here, this is sometimes called a moment matrix. And in the classical theory of optimal design, as a lot of people in the audience know, you tend to use moment matrices. For many reasons. One reason is that the log of the determinant is, you can mix moment matrices. You mix the measure, you mix the moment matrix, and you can do log of the moment matrix. It's a concave function over moments. It's easy to optimize over moments, or measures that way, than having to change the sample size all the time. And that's actually one of the benefits of what I will now, from now on, call convex relaxation. Thank you. So I'm doing this now, but this is fx. This is the integral of fx, and this is this is fg, and this is gg trans. So this is the combined moment matrix from these two models. So I need to stack the f's on top of the g's, and we get this combined model. So what am I going to do? This doesn't mean the London School of Economics. This is just the least squared estimator. So here's the rationale. Remember that I said about treatment to control. We take theta hat to be the classical least squares estimate. I'm not doing it. There's a Bayes version of this. And I want to protect that least squares estimator against phi. That's the job. That's why you're randomizing in clinical trials. You want a protection. So this is all about protecting theta. So if you look at the mean squared error, this should be this mean squared error matrix under the full model. So I'll repeat, I'm doing least squares estimator under the small model, but looking how it behaves under the big model, we get this. There's an n missing. I had an n there, which I've absorbed, and there's a sigma squared, which I've absorbed. So that phi is a sort of standardized phi. So then you go to your experimental design textbook, and you think, well, I want to do optimal experimental design. I want to make m small, because this is a mean squared error, or something to do with m small, and something we would like, something to do with phi to be small, because that's the bias term. So we do optimal design against bias. Now, why is it so easy? Why is it so easy with clinical trials? It's because typically the causal bit, the theta bit, the space is crossed. In some sense, you're crossing the clinical trial with all the other vectors that could be possibly be. And in that case, so there's a theorem. I haven't written down the theorem, but roughly speaking, if you use cross models, you cross spaces and cross designs, then you can do the minimization of the theta bit separately from the minimization of the phi bit. And that's why in some sense it's easy. Well, it's not easy, not that easy. But anyway, here, what you do is you take the trace. Remember, you want to minimize the trace. This is the trace of, sorry, this is I didn't put R in here, so I should say this should be okay. So I didn't highlight this term. I'm going to call S1, and this term I'm going to call S2. They're matrices. You could take determinant. D optimality, or you could take trace, A optimality. And people in the room could mention about 5 different other types of optimality. And I've taken an additive model. I've cheated a little bit because I haven't used the multiplicative. Okay, so if it's trace, I can just add up the traces. And D optimality is a slightly different term. You get a product, sort of obvious. So here we are with trace, 2 traces. We want to minimize the trace of S1, but we got this bias term, and we've got to deal with it somehow. So here's a simple factorial example, just to prove the point. I've even taken a risk here. I put a multiplicative term in between the x bit and the z bit. But even so, I take the product measure. This is a way of, these should add up to 1. So this is just 2 to the k factorial design. It's an easy problem. -1, up to 1, 1. But I'm allowing a sort of rather more generalized definition of a product measure, because this is a product measure. X gets the alphas, and Z gets the beta, weighting, right? So this corner gets 1 minus alpha, 1 minus beta, this corner gets alpha, beta. And now I do the optimization. Here it is. S1 only depends on alpha. Even with this multiplicative, S1 only depends on alpha. And S2 obviously depends on phi, and we can set the bias term to 0, even with this, so if I have a quarter, or one, balanced, I can get this, the bias goes to 0, and then I can do any sort of optimality I want, I can do. So alpha half, beta half, same number of observations over the corner, bias disappears, and I'm just left with the theta term. Bingo, I can do causal theory because the bias is not interfering. Okay, so is that my cup of? Yes. So now the answer to the conundrum and why the gender differentiation for which I shall definitely be sacked. We're going to take a game theoretic thinking. So, just to make life easy, Alice is going to be the causal modeler, and Bob is going to try and get rid of bias. Remember Bob the builder? There's a, Bob the builder. Well, this is Bob the bias reducer. Okay. So Alice, in some sense, plays theta, f, and d1. Her design, and Bob sort of plays bias function d2. Last paper I gave, I had to appoint somebody to count the misprints, but I'm a little bit dyslexic, so apologies if now under the above product conditions, we just shown with the last example that Bob and Alice can work independently. They can really. Bob can do his bias reduction sitting in his gîte in the south of France, right? So, and he's fine, everybody's fine. And that's what the randomization takes place in the basement of the University College Hospital, right? With a coin or something. They probably use a random number generator after 80 years or something. But what happens when they can't operate independently? So now the answer to the question, to the conundrum, is Nash equilibrium. So Nash equilibrium, you all seen the film, is something which you can use when people, this is a cooperative version, when people are sort of in the same direction. It can be a competitive game, but this is a cooperative game, and it's used already in things like aircraft manufacture. So one team is making the engine, wants to make it strong, and the other team is building the airframe wants to make it light. So light airframe, strong engine, you're going to sell your airplane. So there are a sort of policy in which these two things work together. Roughly,
You don't want the frame to be so light that the force of the engine rips the wings off.
exactly. So that's why we have Nash equilibrium, and this is exactly right. So Alice has, this is a general Nash equilibrium statement. So it goes like this. Alice has C1, and she knows that Bob is going to have an optimal, she knows what Bob's going to do and minimizes the cost, knowing what Bob's going to do, and the other way round. All right, so let's see if we can, this is the first time, I hope, a Nash equilibrium has appeared in experimental design. I'm quite proud of that. It took me a long time, long time to find a decent example. Here's one, it works. I had to cheat. That's why this is a very informal seminar. I had to cheat, here it is, like crazy. So, first of all, I kept the product structure, but destroyed the simple factorial tensor structure to apply mathematics, or factorial structure, beloved of everybody. And here we go. I want to find a solution where the partial derivative of S1 with respect to alpha is 0, and the partial derivative of S2, it's my trace, with respect to beta is 0. And so a small perturbation on Alice's solution will get worse, and a small perturbation on the Mr. Bias, Bob the Bias solution will get worse. And here it is. And there is one, I haven't given it, it's sort of, it's not a half. All right? It's not back to the original form. They are different from a half. And here they are. Here are the derivatives. I checked the second derivative to make sure it's a minimum. There's two minimum here and here. You can see roughly 0.4 and roughly 0.6. So now we're in a position to sort of begin to understand bias. Okay, so this is my favorite table. It's produced, you know, took me some time to get this table. It could be wrong, but it's a right idea. So this is, I've taken somewhere back there, I took phi equal to 1, just so we had a basis of comparison, right? There's only a single phi. So let's suppose Alice ignores the bias completely, just uses the d-optimal design for this problem. She does rather well. She does rather well for S1, and not so well for S2, because she's ignored the bias. Here's Nash, somewhat better for S1, and a little bit worse for S1, and a bit better for bias. This DS is wrong, actually. It should be, I didn't want to complicate things. It should be A, it should be the trace. I put D in there just because I like the people in design use DS, it's not, it's the trace. This is the trace for the this is the trace for this is the trace using it's the correct. Okay, I'll forget about this. Let's look at this one. Of course, what you should be saying is I should have used a proper least squares estimator, taking into account the bias. It's unbiased, and therefore the bias is 0. But of course, you're taking into account the biased terms. You don't do so well for the main causal model. So here, you're unbiased, but you've sacrificed. You've sacrificed. So the bias is 0. Great for bias, but the mean squared error for the main model, causal model, has gone up. This This is, I forgot, I suddenly forgot what, that's if you optimize both simultaneously. You put the whole thing in a bag, some criterion, and it's S1 plus S2, and you try and do a whole, and some people in Nash equilibrium compare sort of Alice and Bob operating slightly separately compared to just putting a one big cost function for the whole thing, and that's this one. That's not bad, actually. The other thing we can do, if the paper is written up, we can compare the efficiencies here. We can say compare Nash to the best unbiased estimator, taking into account the bias term. We can compare it. So we can. There's various nice calculations we can do, or we can invent new kinds of efficiencies to measure the contribution of bias. And this is what's held me up. The internal Nash equilibria of the type I'm talking about don't always exist. Typically, you're sitting on a boundary, so they're quite hard to find. All right, let's look at causal parameters.
On
Yes.
that point, is this related to the question which occurred to me when you started describing this, where you said Alice and Bob each behaves independently, knowing what the other does?
That's just what Nash equilibrium is. You imperfect information. You know what they do, but but it doesn't mean to say knowing what you're doing optimally doesn't mean to say I have to do what you do. I don't have to do
it
you.
doesn't mean to say that
No.
each has to do the same thing.
No.
But knowing what the other does means you can choose your strategy, but then the other needs to know what you're doing.
So yes, it's a completely reflexive thing.
So they have to somehow be a simultaneous.
That is what Nash equilibrium is. That's what it's called. That's the name of it. That's why he got the Nobel Prize for showing the existence of such illusion.
Yeah.
So
I was just puzzled about how each can know what the other is.
oh, well, it's abstract. I mean, it's an abstract thing. So I use the telephone maybe. Anyway, this is more standard. This is a treatment control. So with treatment and control, here we have you've got two treatments and control, and you've got all these bias parameters, and I've got one bias term. And elementary statistics says that the least squares estimator of the treatment difference is the difference in the least squares estimator of the individual theta. You can just subtract it, work it through, and you get the bias is 0 when what Alice gets, the mean of what Alice gets is equal to the mean of what Bob gets. So same number of red-headed people in each group, right? The mean of the phi parameter equal, and that's just clinical trials. Here's an interesting thing, which I'm trying to get some papers on. I think there are some, but haven't quite tracked them down. Now let's suppose that Alice has a more complicated model. What the condition for the bias term to disappear is that the individual means, and then this is what statisticians would call the quadratic effect in zi's driven by the model in x's to get orthogonality. All right, so linear and quadratic z contrast should be 0. Because we've got this other term, we need a more complicated sort of matching than just the means are equal. Okay, so this leads. I was going to draw a picture. Maybe I will still draw the picture. So there's a lot of stuff on matching, and what they do in social science, in order to produce this orthogonality, they just take in your big data set. In your big data set, this is the biggest data set I have. This one right here. And let circle be the treatment. So you find something close in Z space and give them the control, so that they're roughly orthogonal, just like so it doesn't really matter then which model you fit in X's, because you're pairing off, you're getting all the right term, like so if it's a quadratic one, if it's quadratic, then we'd better have these ones get when x is -1, you give these. When x is say 0, you get these, and when x is 1, you get these. So roughly speaking, in Z space, this plus this minus twice this is 0. So that by that complex matching, and that's basically what they do in some kinds of social science. But now I'm going to switch a little bit, and let's just have a kind of summary. So Alice and Bob, I'm taking a bit of a breather on this slide. Alice and Bob working together against nature, which is a hidden source of bias, and they're going to play cooperative Nash games. That's the idea. The whole history is bedeviled by the following fact. You've got two sources of randomness. You've got the errors you've been hearing all week, and the randomization distribution. So if you have to work to play those two things off against each other. I've talked about, so for randomization, so I'm now going to put in University College and the economics department at LSE even closer together, because in the University College, they sort of, I'm going to do randomized clinical trials, right? Randomization in economics is called, or game theory, is called a mixed strategy. So basically, the people in clinical trials are using a very primitive version of a Nash equilibrium, because the simplest version of Nash equilibrium is simple minimax. They're minimaxing against these things which are going to hit you from outside, like the redhead effect. My mother was redheaded, so and one of my major points is that to play these games, you need to have some background idea of what it is going to hit you. Otherwise, you just have to have simple randomization. But if you have some, like, a good example is stratification. You stratify by age, and you randomize within each strata, and then subtract. Okay, so that's a more sophisticated type of randomization. And because of the called crossing theorem, where they work independently, it all becomes too easy. The optimal design theory doesn't penetrate in because it's too easy just to randomize. Okay, so that's another point I'm going to make. So here we are. The poor old Bob is going to have to do the randomization, all right? He's charged. He's going to have to pay randomization games, or he can either stick with the model, and then he can, forget about mean squared error. I'm going to minimize this matrix. I'll take the maximum eigenvalue of my Q matrix. Nobody tells me how to reduce bias. I'm going to do what I want. I'm going to have a ball, a little bit like in the numerical analysis. I'll have a ball for my phi's. I'll minimize some norm, and that's me, and I'll go home. Or, when he's vaguer, he doesn't really know what the model is, just some functional class. Well, then it becomes very difficult to do. He could do mixing, but he doesn't really know how to set up the mixing. It's when he's vaguer, when there's some content to the bias model, but not enough to model it, and not enough to even get a hold of it here, he'd better takes his favorite criteria, maybe a simpler version where this is in some function class, and he wants to reduce the maximum of this, of function class. There should be a max z, or this is the probability of the deviation. This is the sort of thing you do in numerical analysis, where you actually use the randomization distribution to go. You look at the expected bias, if you want, and minimize that. But it's that where you have to play not this more physical Nash equilibrium, but the proper randomized, proper old-fashioned randomization. You see, for years, I was very snooty about randomization, because people came up and said, "Oh, randomized blocks. You know, I've got to have block. You have a block of. On day one, I'll mix up all the and have a randomized block." And why? Well, that's right. That's a strategy. You know, so I'll come back to these points later. So this is Bob. So there's a lot of work to be done by Bob if he's going to really play randomized mixed strategies of a Nash type against nature. Now I'm going to. How long do I have?
I've got 10 minutes.
Okay, I'm just going to go. I'm going to teach causal. This is the world record for teaching causal models in statistics. All right. So I better speed up. I need a cup of coffee. So we need a DAG. Oh, this is a DAG here, right? The DAG is loved by social scientists and lots of artificial intelligence, Perl, DAG models. You think the arrow means A causes B. Yeah, it's more complicated than that. It's just conditional independence models and stuff going on with DAGs. That's okay. Some people spend a lot of time on DAGs. There's a DAG group. There's a causation, social science causation group, which means every so often, occasionally. And this is quite an easy case. This is an easy case. Theta naught sort of x naught sort of causes x1 causes x2. And you've got some parameters which measure the strength of causation in some sense. And here, this is quite an easy case. This is the killer case. This is called a collider when you have x1, x2, where you have this kind of reverse errors. Complicated, long history, lots of new theorems, lots of algebraists working on it. Very, very active area. There's a harder case where you've got this causation, then you've got this long loop. I'm trying to prove that y causes z, really. So there's a long loop here, and other loops, and so very complicated. You have to really take Pearl's book back for the weekend, and then you still don't understand it. Some rules. There's rules to get causation. You've got this d-separation. You must not only condition on that, you need to condition. So the rule of in inference is you must fix something, otherwise you get all these backdoor causal structures. You need to kill them off, right? So it's not enough just to condition. You must have a protective, what's called a protective blanket, stopping these feedbacks, all right? And the question is, I'm asking everybody, if we're going to go into big data and build causal models, we better know something about, if we're going to use experimental design in causal models for big data, we better know something about experimental design for causal models of medium size, okay? So, there's an easy way to set it up. Easy way to set it up. It's just I wouldn't even do it, but I mean, here's an easy way. You just say, oh, when I go from y to z, just add a fixed parameter. That's at least looking linear. But if you say that x10 is theta 9 times x9, and you propagate that back all the way through, it's a non-linear model. Only in very simple case like this, it's additive. Is it a traditional linear model amenable to optimal design? So we had lots of talks on optimal design for nonlinear models. A DAG is a nonlinear model. So that's wide open to do experimental design for DAGs. Absolutely wide open. So we can use, it's more like, the full approach is more like an autoregressive process, and the hours are just the hours, the forward hours of an autoregressive process. I've called it here a big AR. It's a big AR, you know.
Yeah.
It could be time, but it might be called. And there is, of course, the backdoor theorem. So I was in, most of it, I was in Oberwolfach talking to algebraists, and I said, this backdoor theorem is Pearl's, where in order to get causation, you must stop the future affecting the past. You can't have causation if the future affects the past, or the forward variable affects it. And that's exactly Granger causation. I think he got the Nobel Prize for testing for whether it was feedback free or not. So we must have feedback free. You could think of that as another source of bias if we don't get it. So we need feedback, you know, and this is all, and whether observing and controlling are the same thing. Huge debates about that. But so after I've done all the conditioning in that last example, now I can be causal, you know, because I've got nice chains going back. So that's a little example where I was able with the right conditioning. But there's a snag. And these are the big issues. Forget about this. Forget about AR. Observational studies, and I almost had a discussion with Dave about whether, Dave said earlier in the week that experimental design is intervention. You condition on something, but you could just observe it also. Yeah. But here's the key. Here's the key. Where do we use part one? Where do we use all these Alice and Bob tricks? We need it to produce, to protect, where are we? To protect all these variables here, because you can have a hidden confounder coming in here. What do they actually do in practice? They say, what about hidden? Oh, we randomize. And what they're really doing is protecting the back door. First of all, they condition but they're protecting the model from hidden confounders. They talk hidden confounders, but they don't say they're going to randomize. There's no theorems on randomization in causation, really, and they certainly don't use Nash equilibrium. They don't say they're playing randomized games against nature to protect causal models. And that's the main message. Far from not liking randomization, the claim I'm making is that randomization is Custer's last stand for attacking big data. You need it. We need that matching. Or you can do matching, of course. Or we need matching and all these techniques in order to protect the causal models, whether it's a simple treatment to control. We need to protect the causal models from the hidden confounders lurking in the undergrowth. The crocodiles are going to bite you. You need randomization to attack that. So this is how to do DO in DAG. You need to eliminate bias, condition to close the back door, and then once you've done that, you can do any optimal design you want. Anything. You can do observational optimal, or D optimal, A optimal, but you must have those initial protection first. Close the back door and eliminate bias. That's the end. I'm stopping there because I'm exhausted.
Do we have time for questions or comments?
One comment which occurred to me fairly early on, supposing the availability of data is dependent on something which is relevant to the investigation.
Oh, that's covered by the theory. That's really covered by this backdoor condition. You must note what it is and then make sure that it does not. And that is exactly, well, somebody may correct me, but that's almost exactly what Pearl said. You mustn't have things, for example, certainly if Y is causing Z, you mustn't have Z being mustn't be able to trace Z to another variable all the way back to some of the causal
It's not
variables.
a case of tracing it to a variable. I was talking about the availability of the data, that the individuals who can occur in your data set are influenced by some relevant variable.
But you,
There's one very simple but quite dramatic example which I use for this sort of thing. It is the estimation of the population of fish of a certain species in a pond using the method of capture and recapture.
yes,
If the fish are not equally catchable,
right,
then the population estimate that results
yes,
estimates the catchability weighted population.
Right.
Each fish is multiplied by its catchability.
well,
And the extreme example of that is all the fish but one, when they see the capture people coming,
yes,
dive down and hide in the vegetation at the bottom of the pond. And there is one fish which loves being captured,
well,
and is always captured, and then the net result of that is that the estimated population of the fish in the pond
Yes.
is one.
I can't answer that question because I would need to do the math, even if I could do the math. But there's one it gives me opportunity to mention one technique which I have not mentioned, which tries to correct for sampling bias of that nature, and that's called propensity score. It's a bit like matching, but harder to understand. So that's been thought about, this sampling bias, because something relevant is more likely to be sampled, and that's what propensity score, Rosenbaum's propensity score. Incidentally, I do have. This is that stuff. There's two. When I'm thinking about this, there's some great recent papers on experimental design for big data. This one's statistical science, and this is our one. And Doug Wynn has done a lot of stuff. My little bit of maths is very close to what he did. I mean, the paper I'm talking about is this is the famous paper, which does propensity score and artificially in a way corrects for the the phenomena you're talking about.
Any other questions?
So if big data is there and the model can be created,
Yes.
and bias can be understood and eliminated to a degree,
Yes.
then in engineering I would then confirm my hypothesized model by
Yes.
running confirmation runs.
I
So would you then go back to the big data set and hypothesize that your model that you've created would then match your prediction?
Yes, I mean, if it was in engineering, you could do a confirmatory experiment, or a computer experiment. Yeah, absolutely. It's a bit tricky when you're dealing with people, but you might build a council block and put what you decided in, and all your smart meters and stuff, and then see that if the residents were happy from what you got from your causal model. Yeah, you should always confirm if you possibly
I
can.
mean, it sounds a little bit like going back to agricultural experiments and repeated measurements, and that you can't do something for a long period of duration of
Yes.
time afterwards to then go back and check. And
Absolutely,
then that brings
yes.
another issues
Yes.
with repeated measures.
Yes, I mean, I could have probably done that. Well, slightly related to that is the FDA now has regulations for doing repeated experiments, and the really hard thing is if you discover a new variable halfway through your repeated measure, suddenly red-headed people appear, or sorry about red-headed, and they've got to be biased. We better start the randomization against hair color halfway through. So I didn't mention dynamic experiments. There's been a lot of stuff in dynamic experiments in this workshop, and it's called sequential randomization, and it's unbelievably difficult. In fact, the one paper on Nash equilibrium in the randomized trial does it over time. So that's a sequential game. sequential randomization equals sequential game theory. So there, LSE and had really better get in there and start looking at sequential experiments as randomized games, if they're using randomization.
Any other questions? I just had a quick question. So that the first work that I know that started looking at how to design the bias was the original Fox and Draper paper.
Yes, very famous.
So I was wondering, how does that fit into the sort of...
Yes, in fact, I quoted Val Fedorov, and somewhere I used Val Fedorov's paper somewhere here, and yes, they quote those. You're absolutely right. There's not terribly well known, but there's a whole sequence of papers doing my split basically, and whether I should go arguments about whether they can optimize. The trouble is, it's not a convex problem. So you could think of what I did there as a solution to the Draper paper, acknowledging the non-convexity of the Vox-Draper approach. So absolutely, yeah, it's a foundation paper, and I should have mentioned that.
Right, well, let's thank Henry again.